Every successful application eventually faces the same challenge. As more users join and more data flows in, the system starts to strain. What once worked smoothly for 1,000 users can begin to crack under the pressure of 100,000 or even collapse at 1 million. This is where scalability becomes absolutely critical. Scalability is the backbone of any robust system, ensuring that as demand grows, your application can keep up without a complete overhaul. In this video, we'll explore what scalability means, why it's foundational to system design, and how it sets the stage for availability and reliability. Let's dive in and see how to build systems that grow with your ambitions. Scalability is the ability of a system to handle increased load simply by adding resources. The key word here is ability. A scalable system can grow to meet demand without needing a complete redesign. This concept is foundational in system design, influencing how we achieve both availability and reliability. When you understand scalability, you're better equipped to make decisions that keep your system healthy as it grows. In the next scenes, we'll break down how to measure scalability and why it's not just about adding more servers, but about making smart, strategic choices. Before you can scale, you need to know what to measure. Vague statements like "we need to scale" don't help unless you have concrete numbers. Scalability is typically evaluated along several dimensions: requests per second, concurrent users, data volume, throughput, query rate, and message rate. For example, you might track how many API calls your system handles per second or how much data is stored and processed. By understanding these metrics, you can pinpoint where your system starts to struggle and make informed decisions about scaling. Let's look at each metric in more detail. Load metrics are the backbone of measuring scalability. Requests per second (RPS) tells you how many API calls your system handles. Concurrent users show how many people are active at the same time. Data volume measures how much information is stored or processed, while throughput tracks how much data moves through your system per second. Query rate and message rate are especially important for databases and message queues. By monitoring these metrics, you can see how your system performs under stress and identify which parts need attention as your user base grows. Scalable system isn't just about handling more users, it's about maintaining good performance as the load increases. Ideally, as you double the load, response times should only increase slightly or even stay the same if caching is effective. But if response times spike or the system starts timing out, you've hit a scalability wall. The goal is to keep performance stable with linear or sublinear degradation. This means your system can predictably handle growth, and you can plan upgrades before users feel the pain. Vertical scaling or scaling up means adding more power to your existing machines. This could be more CPU cores, more RAM, faster SSDs, or better network cards. It's often the first response to performance problems because it doesn't require changing your architecture, just upgrade to a bigger machine. Vertical scaling is simple and can be effective, especially for databases or early-stage startups. However, it has limits: hardware caps, single points of failure, and higher costs for bigger machines. Let's explore when vertical scaling makes sense and when you might need to look elsewhere. Vertical scaling is attractive because it's straightforward: just move to a bigger machine. The pros include simplicity, lower latency since all data is local, and no distributed system complexity. But there are significant downsides. You're limited by the largest machine available, there's a single point of failure, and costs can rise quickly. Plus, upgrading often requires downtime. Many real-world systems run on vertically scaled databases for years, but it's important to know when to switch to horizontal scaling for continued growth. Vertical scaling works well for databases where data locality is important, applications with strong consistency needs, and early-stage startups that prioritize simplicity. It's also suitable for workloads with predictable, moderate growth. Never dismiss vertical scaling as not scalable. It's a practical solution for many real-world scenarios. The key is knowing when your needs outgrow what a single machine can provide, and being ready to transition to more advanced strategies when the time comes. When vertical scaling hits its limits, horizontal scaling or scaling out becomes essential. This means adding more machines instead of upgrading a single one. Companies like Google and Amazon use horizontal scaling to handle billions of requests. A load balancer distributes incoming traffic across many servers, each working together to serve users. This approach removes hard limits, improves fault tolerance, and can be more cost-effective. However, it introduces complexity, especially around data consistency and network communication. Biggest advantage of horizontal scaling is that there's no hard limit. You can keep adding servers as needed. It also improves fault tolerance, since if one server fails, others keep running. Smaller machines are often cheaper than one giant server, and you can distribute them geographically for lower latency. On the flip side, distributed systems are harder to build and maintain. Keeping data consistent across servers is challenging, and network overhead can add latency. Stateless application design is usually required, which may mean architectural changes. Horizontal scaling to work smoothly, services should be stateless. A stateless service doesn't store session data locally, so any server can handle any request. This allows the load balancer to distribute traffic freely, avoiding hotspots and making it safer to add or remove servers. To achieve statelessness, store session data in shared caches like RIDIs, use tokens instead of server-side sessions, and keep files in object storage. This shift is crucial for scaling out efficiently. Application servers are usually the easiest part of a system to scale horizontally, especially if they're stateless. Key strategies include making services stateless, using load balancers, auto-scaling based on demand, and deploying across multiple availability zones. This approach allows you to quickly add capacity during traffic spikes and ensures high availability. By focusing on stateless design, you make it easy to grow your application tier as your user base expands. Databases are often the hardest part of a system to scale because they manage state. Unlike application servers, you can't just spin up more database instances and put a load balancer in front. Data consistency, durability, and transaction isolation all add complexity. The right scaling approach depends on your workload. For read-heavy workloads, red replicas can help. For high write volumes, sharding or moving to NoSQL databases may be necessary. Let's break down these strategies next. Read replicas are a common solution for scaling read-heavy workloads. The primary database handles all writes while replicas serve read queries. This setup is simple to implement, especially with managed services, and can dramatically increase read capacity. However, it doesn't help with write-heavy workloads and introduces replication lag, meaning some reads may be slightly stale. Still, for many applications, this trade-off is acceptable and provides a big boost in scalability. Read replicas aren't enough, or when write volume is too high, sharding becomes necessary. Sharding splits your data across multiple databases based on a partition key like user ID. This distributes both reads and writes, allowing you to scale horizontally. Sharding is powerful but complex. Cross-shard queries are expensive, and rebalancing shards can be operationally challenging. Common strategies include range-based, hash-based, and directory-based sharding. Choosing the right approach depends on your data and access patterns. SQL databases like Cassandra, MongoDB, and DynamoDB are built for horizontal scaling from the ground up. They offer built-in sharding, eventual consistency, and flexible schemas. NoSQL is ideal for workloads that need to scale writes and handle large volumes of data. However, they require different query patterns, often lack joins, and may provide only eventual consistency. For many modern applications, NoSQL databases are the backbone of scalable, high-performance systems. Caching is essential for reducing database load and improving response times. A well-designed cache can handle 100 times the throughput of a database. Redis, for example, can process over 100,000 operations per second on a single node. Scaling caches involves using Redis clusters, consistent hashing, and the cache-side pattern. By serving hot data from memory, you keep your system fast and responsive, even as user numbers soar. Message queues are vital for scaling asynchronous workloads. They decouple producers from consumers, allowing each to scale independently. Queues also buffer traffic spikes so consumers can process messages at their own pace. Technologies like Kafka use partitioning to enable parallel consumption. By introducing message queues, you make your system more resilient and flexible, ready to handle unpredictable traffic patterns. Let's walk through how a startup might scale a social media app from zero to millions of users. At launch, everything runs on a single server, simple and cheap. As users grow, the first bottleneck is resource competition between the app and database. The next step is separating the database onto its own machine, tuning each component independently. As the user base grows, adding a cache layer like Redis dramatically reduces database load. Eventually, the single app server becomes the bottleneck, leading to horizontal scaling with multiple app servers and a load balancer. As the system grows, adding more app servers is easy, but the database becomes the next bottleneck. Read replicas multiply read capacity, but eventually write throughput hits a wall. At the stage, sharding is introduced, partitioning data across multiple databases. This distributes both read and write loads, but also brings complexity. Many teams consider moving to distributed databases that handle sharding automatically. Each scaling stage solves a specific bottleneck, allowing the system to handle millions of users. Scalability is about designing systems that grow with demand without falling apart. Vertical scaling is simple but limited, while horizontal scaling is complex but nearly limitless. Different components require different scaling strategies. App servers are easy to scale horizontally. Databases are much harder. Always identify the bottleneck before deciding how to scale. Common patterns like load balancing, caching, and async processing appear in almost every scalable system. But remember, a scalable system isn't useful if it's not reliable.